Hello friends, so today few questions, and these questions are from, you can say, some variable mass, okay, and the conservation of momentum. Okay, so total 5 questions we are going to solve, and so in the first question we are given that a plate of mass m moves horizontally with a speed v on a frictionless table. A mass m is dropped vertically on the plate and eventually comes to rest relative to it. What amount of energy must be supplied to the combined system to restore its horizontal speed to v? Okay, so it means we have to come back to the original speed v when the mass small m and capital M are combined together. So you can just draw the basic diagram also. Suppose this is your plate having mass m and it is moving with the velocity v. At some point of time we are adding to it or dropping on it a small mass m, and because of this now these two will be traveling together or moving together. So this will be m plus small m. So obviously the mass is increasing, so their velocity is bound to change. Okay, so let us assume that now their velocity is our u, but we want that these two should be once again traveling with the velocity v. Okay, and for that we have to supply some kind of energy to it so that the entire system is once again is traveling with the velocity v. So this is the basic question. So in this case we are going to use the conservation momentum, and let us start with our initial state. So initial state is only our this mass m, and final state is our combination of both. So we start with our initial state. And initial state is our before the mass is dropped. Before mass is dropped. And for that we are given that the mass of the plate is given to us as capital M. It is moving with the velocity of our v. Okay. So you can say plate speed is given to us as v, and we have to remember that this mass small m is dropped vertically. Okay. So which basically means that this is having zero horizontal speed. Okay. So we have to keep this in mind, and for that we can say that our dropped mass m, it is having zero horizontal velocity. Zero horizontal velocity. Therefore, we can say our initial momentum let us call this as P of I is equal to our capital M times V, and our initial kinetic energy let us call this as K of I, and that will be equal to over half M V square. So these are our two initial parameters. And then it is given that as soon as this mass small m is dropped on the plate, they stick together. Okay? So they are moving, and this you can see in the fraction of a second they stick together. There is no as such delay between the two. So we can say that dropped mass sticks to plate immediately. And it is also given that our table is frictionless, so therefore the horizontal momentum is conserved. You can say that our horizontal momentum is conserved. And like I said, we assume that their common velocity, that which we are moving, is our u. So the final momentum will be equal to m plus small m times u. You can say that our final momentum, that is a p of f, will be equal to m plus small m times u. And then we can use the conservation of momentum. So we can say our P initial is equal to our P final. And so we can write it as substitute the values, and P initial is our MV and our final is our M plus small m times u. And from here we can find out our u is equal to our m plus small m times v. So this is our final velocity when they are both traveling together. And the collision is basically inelastic because the plate, the mass sticks to the plate. So you can say that the kinetic energy after inelastic collision, let us call the final kinetic energy, and that will be equal to half summation of their masses and u square, the speed with which they both will be traveling. And we can substitute value of u, so we get our final kinetic energy is equal to half m plus small m, and u is our m plus small m times v. and this is our square and this is also square. So here this will be also giving us square, so let us write it separately. And because of this square, this m goes cancel with this square, so we get this will be equal to half m square m plus small m and v square. Now we have to make sure that our kinetic energy is, or we can say the energy restored, sorry, not energy, but speed is restored to v. Okay. So we need that speed should be back to v. So we can write energy required to restore speed to v. So it means the desired kinetic energy let us call this as kd, should be equal to over half m plus small m and v square, because we need that a velocity should be equal to v, not equal to u. So this is our desired kinetic energy, and from here we can write that energy that must be supplied, let us call this as our delta E, and this delta E will be our desired minus the final kinetic energy. Okay. So we simply substitute it, so we get our delta E, desired is our half m plus small m v square minus, and our final kinetic energy is half m square m plus small m and v square. Okay. Now it is quite easy, it is simple mathematics now left. Therefore we can take our half v square common, and we are left with m plus small m minus m square and m plus small m, and we are going to take now LCM and sort it out. So we get this as half v square, and our LCM will be over m plus small m. So obviously here it will be coming as m plus m whole square, which we can open the square directly, so we can write this as m square plus small m square plus twice mm minus m square, and this m square and m square cancels out, and we can take this m common from both, so we can write that our required energy that will be supplied, we can write this as our half m v square, and this can be written as m plus twice m and m plus m. Okay. So this is the amount of energy that is to be required, or that is required, so that the final velocity, which was our u, comes back to our v. So this was our required energy. And okay, so this completes the first question. Now we come to the second question. And this second question is based on the variable mass. There is some of the questions which we did yesterday also in the last video, and all these masses which we did yesterday was in vertical part. Okay, now this one is in the horizontal direction. Okay, the rope is moving in the horizontal direction. So it states that a rope of length L and linear mass density rho lies fully stretched on a smooth frictionless horizontal table. One end of the rope is pulled back parallel to itself, starting from rest. Your hand moves with constant acceleration A. What is the force exerted by your hand just before rope becomes completely straight? Okay. So this is basically our variable mass system. And in case of variable mass system, like we discussed yesterday also in the last video, that we said that we cannot apply directly, or rather we can say we cannot apply the formula force is equal to mass into acceleration. Okay, because the mass is going to change, okay, as it is going to be pulled with our certain force, which force is F. And in order to sort it out or solve it, we are going to use the formula with respect to, that is, a rate of change of momentum, because we know that force is also our rate of change of momentum. This thing we have to keep in mind, and this is true for whether we are moving this variable mass in the vertical direction, or in this particular case, like we are moving in a horizontal direction. So this formula, that is summation of forces, will be equal to rate of change of momentum. So before we start the solving this this particular question, here we have to remember one important part, that, okay, let me draw the figure first. So this is the length L of the rope, and to one of the end we are pulling it in this direction so that they move in parallel to each other. Now here we have to just remember one thing, that if the length of the rope that is pulled back in the reverse direction, if that is x, then the same length will be of our unpulled rope also. Okay. So which means here it is given as L, but we are going to write a general equation with respect to x, then we easily convert this with respect to L. So which means that suppose the length that is pulled back is our x, then the length which is remain to be pulled back is also our x. Okay. So that this total length comes equal to 2x, but the actual length of the rope cannot be greater than or less than L. Therefore we can say this 2x will be always equal to our L. From here we can say that our x will be equal to L by 2. Okay, this we have to keep in mind. Okay. And here in the question it is mentioned the term which we are more interested in, completely straight. So this concept is based on the completely straight. So it means the term completely straight basically means that the folded part reaches the far end of the rope. So we can just define it, that our completely straight means that folded part has reached far end of the rope. Reached far end of the rope, and all the rope will be moving in same direction without any fold under this condition. So furthermore we can write that all of rope is now moving in same direction with no fold. So based on this, we found out that the x is nothing but the displacement of the hand. Therefore, we can say that hand displacement which is our x is equal to our L by 2. And now we can use our equation of our kinematics. So we can say that it is given in the question that the hand starts from rest, okay, and moves with a constant acceleration a. So therefore, if its final velocity is v, so we can write that our hand starts from rest with acceleration a. Therefore, we can write that our v square is equal to our 2a and our L by 2, which comes as a times L. And please remember, this is just before complete straightening. In the question itself it is mentioned that we have to solve it just before it becomes completely straight. And we are given that it is having mass density of our rho. Therefore, we can write that total mass of the rope suppose that is capital M, which will equal to rho times L, because we are given that it is having a density of linear mass density of rho, okay? Or we can say force per unit length. And now we are interested in finding out the forces that will be required, and these forces, or we can say, we are going to provide the forces for two different reasons, okay, or we can say we can divide it rather. So we can say that a force is required and these forces should be because of two reasons. Or two reasons basically means we can divide our applied force into two types, whose summation will be giving us the total force required. The first one is our accelerating the rope already in motion. Accelerating the rope already in motion. Okay. And let us call this force as F1. So F1 will be equal to our mass. Mass we know is our rho times L, and acceleration is our A. And the second force which we are going to find out is that will be, you can say, supplying the momentum to the newly moving rope, because the rope will be continuously in motion. So the second part will be supplying momentum to newly moving rope. and we have to pull the rope until its velocity becomes equal to v. Therefore, we can say that our F2 will be equal to our rho times v square. Okay, in terms of momentum, we can easily say that it is, or we can say the required force equals to the rate at which momentum is added. So, basis of this equation, we can write that our force equals the rate at which momentum is added, which will be giving us rho v square. Okay. But we know that our v square is nothing but a times L. So we can say that our F2 will be equal to rho a times L. So we got our 2 times of forces, so which basically means total force exerted by hand which we have said is a F, will be equal to the summation of these two forces. And we simply substitute the values, so we get F is equal to, we have 2 rho AL plus rho AL. This gives us that applied force F is equal to 3 rho AL. So this is the applied force, so that the rope becomes just straight. So now we come to our third question. So in this question, it is said that a rope with linear mass density rho lies in a loose heap at the edge of table. One end of the rope initially extend an infinitesimal distance beyond the heap. You grasp this end and pull it downward with the constant acceleration A. Assume that there is no friction between the different parts of the rope as it unravels. So based on this, we have these two questions. As a function of time, determine the force exerted by your hand on the rope, and part B, find the value of A. A is our acceleration, for which the force applied by your hand is identically 0 at all times. Okay. So we can just draw the basic figure. So suppose this is the table, and on this table we have kept a rope, and that rope is something like this in terms of heap, and one end is slightly outside, and we hold this end and start pulling it downward. Okay. Or we can say we jumped from the table holding the end of the rope, so the rope will be traveling along with us. Okay. So it will be moving something like this in the downward direction along with the person who jumped with the rope, and it says that is pulled downward with the acceleration of A. So it is pulled downward with the acceleration of A. So we have to keep in mind that we are pulling this rope continuously vertically, okay, in the downward direction, not in upward direction, or neither there is a free fall of the rope. Rope is being continuously pulled downward with the acceleration of A. Okay, so we have to keep this in mind. Later on we are going to use that also. So we are going to solve part A. And part A, we are going to use the kinematics equation, and it is said that the rope initially was at rest. So we can say that our starting from rest, with constant acceleration a. With constant acceleration of our a. Therefore, at any time t, you can write the velocity equation. So you can say for time t, we can say that our velocity at that time t, initially at a rest, so this will be a v of t times at, and the distance pulled down for this time t, let us suppose that is our y of t, that will be equal to over half a t square. And so this distance y of t that is being pulled down, this will be same as the length of the rope. So the length of the rope will be same at the distance it has been moved. Okay. Suppose at certain time t, this is the position. So this is our y of t, which is nothing but our length of the rope. And here we are having the velocity as v of t. Now we are going to find out the mass of the moving rope. Mass of moving rope. And same time t, okay, let us call this as our m of t. Then this m of t will be equal to the linear mass density rho times the length of the rope, that is y of t. So this gives us half rho a t square. Okay. So at this particular time, this entire mass is our m of t. Now, because as the rope is going to unravel itself, its length is going to increase. Obviously, its mass is also going to increase, or we can say it is a variable mass system. So you can say that variable mass system, and we are going to use the momentum here, and the basic equation of momentum is equal to P is equal to m times v. So we can write, or we can simply differentiate it with respect to time t. So we get this as dp to dt will be equal to our mass and dv by dt plus v d by dt, and our this dv by dt is nothing but our acceleration, and our dm by dt is nothing but our rho times v. Okay. Or we can say this is rho times a t, because we already know velocity we just calculated is our a times t. Therefore, we can say that our dp by dt is equal to, we already know the mass is our half rho at square. Okay. So we can write this as our half rho at square, and dv by dt we put a, and this v is our at, and dm by dt is our rho at. And so this will be our half rho a square t square plus, we get this as a rho a square t square, which will be giving us 3 by 2 rho a square t square. Okay. So this is our rate of change of momentum. Now we come to the forces, because we are going to use that the summation of the forces is our rate of change of momentum. So we are interested in the forces, okay, which then we are going to algebraically add them and sort it out. So we can say that the forces on moving rope, forces on moving rope, and downward we are going to take positive. Okay, so it is moving downward and we are going to take it as a positive. So obviously one of the force that will be a force of gravity that will be moving on the moving rope. So first will be of gravity, or we can also see it as weight, gravity on moving rope, and we can write this as our f of g, which is equal to our mass times g, and this mass is our m of t, which we have calculated is our half rho at square. Therefore we can write this is equal to our half rho a t square times g. And the second one, the force exerted by the hand on the rope, okay, and that will be in upward direction. And the second one will be force exerted by hand on the rope. So gravity, this f of g will be in downward direction, and we say this is our f of t, and this will be in upward direction. So therefore summation of these forces is equal to rate of change of momentum, and we can write summation of forces is equal to dp by dt. So we get our mg minus f of t is equal to 3 by 2 rho a square t square. Okay. And we can easily find out that our f of t is equal to, so in place of mass we are going to put it, but let me write it first, a square t square minus, and our mass is half rho a t square minus half rho a t square times g. And we can sort it out further. We can take 1 by 2 rho a t square common, 1 by 2 rho a t square common. So this comes as our, one second, I've written sign is wrong. This is minus and this is plus. Okay, left right, and we get this as our g minus 3a. So this is our force on the hand. That's our first part. Second part is quite easy. We can simply find out from this particular equation. So we have our part B, which states that acceleration for zero force. So what we want, that the force to be zero at all times. Okay. So we simply equate this equation equal to 0. So we want force should be equal to 0 for all time. So which means that this half rho at square cannot be equal to 0. Only possibility is g minus 3a is equal to 0. So if we get here g minus 3a is equal to 0, giving us that our a is equal to g by 3. Okay, for this particular value of acceleration, our force will be 0 for all times. Next question. It states that a rope of mass m, length L, lies in a heap on a smooth floor with one end attached to a block of mass m. The block is given a sudden impulse and instantaneously acquire a speed v0. Let x denote the distance travelled by the block. Assuming there is no friction, neither between the rope and the floor, nor within the rope itself. Determine the tension of the rope at point P just to the right of the heap as a function of x. So basic figure is given to us. So initially this is our rope lying in a heap connected to mass m, and suddenly we are giving it an impulse, and in the fraction of a second it is attaining a velocity of v0. After some time, the length of the rope is our x. At this particular moment, the point that is very close to this heap is called as P. Okay, and we have to find out the tension of the rope at this particular instant as a function of x. So in terms of the length x. So once again, we have to remember that this is a variable mass system. Okay. And under this condition, we can say that first of all, let's find out, or rather we can say that the linear mass density of the rope let us suppose that's our lambda will be equal to our total mass m and total length L. And it is given that the distance moved with the mass is x and the length of the rope is also x. Okay, because the block has moved a distance x and the length of rope is also x. From the figure we can just make this conclusion. So we can find out that the mass of the moving rope, or let me write it out, that the length of the rope moved is our x. Therefore, we can say mass of moving rope let us call this as our mr, and that will be dependent upon our x. So we can write this our linear mass density multiplied by x, which we can write as our mx upon L. So it means we found out the mass of the moving rope, and we also know there is a block which is having a mass capital M. Therefore, the total mass moving mass, let us call this as mt, that will be dependent upon x, will be equal to block mass, and this our rope mass, that is our mx upon L. So this is the total mass at any instant x. Now we are going to find out the velocity of block as a function of x. Velocity of a block as a function of x, and we have to remember that blocks have moved a distance x, okay, and started from rest, and there is no, as such you can say, there is no external horizontal force, only a small impulse is applied. Okay, so obviously the horizontal momentum is going to be conserved. You can say that there is no external horizontal force. Therefore, you can say the horizontal momentum is conserved. Momentum is conserved. Okay. And let us find out the initial momentum. And the initial momentum will be only associated with the mass, because for the fraction of second only the mass is attaining the velocity v naught. Okay. So you can say initial momentum, that is our p naught, will be equal to m times v naught. Okay. And the momentum at displacement x, which will be our final momentum. So we can say that momentum at displacement x, we can also call this as a final momentum, which will be equal to mass of the both blocks, block and the rope, and the velocity at that particular moment. Let us call this as v, and that will be our dependent upon x. And like we said, the momentum is conserved. Therefore, we can say our p initial is equal to p final. P initial is pi. So we get this as our m v naught is equal to m plus small m, and this comes as our v of x. Okay, so though from here we can easily find out our v of x, that the velocity at the distance x will be equal to m times v naught, and this comes as m upon l n x. This is the velocity at the distance x. Now we are supposed to find out the tension at point P. Okay. Therefore, we can say that tension at point P. And tension at point P means when the distance is x. Okay. Or we can say that the rope is moved continuously from rest into motion of speed v of x, which we just calculated. Okay, so it means the tension or the force will be equal to the rate of momentum transfer. So you can say that at point P, rope is continuously being brought from rest into motion at speed Vx. Therefore, we can write the tension equals the rate of momentum transfer, rate of momentum transfer to newly moving rope. Newly moving rope. Okay. So which means that it will be the tension that will be forcing the rope to move. Therefore, we can write that tension T will be equal to our lambda v square, and lambda we already know is our m upon L times v square, and this v is nothing but our v of x. So we substitute it, we get this as our m of L, and this will be m v naught m upon mlx and its whole square. Okay. And there is no need to solve it further, we can just keep it as it is. Okay, so this will be the tension in the rope at point P. Okay. Next question. It states that a dustpan slides down a plane inclined at angle theta to the horizontal. Dust is uniformly spread over the surface of the plane, and the dustpan continuously collects the dust along its path. Assuming there is no friction between the dustpan and the plane, determine the acceleration of the dustpan. It has been sliding for a long time. So it means this is also a variable mass question, and here variable part is the dust that is being collected continuously by the dustpan. Okay. As it is going to move further down the inclined plane, more and more dust will be collected by the dustpan. This is basically a variable mass question. And for variable mass question, we already said that we are interested in using the formula, or rather we can say we are compelled to use the formula with respect to the rate of change of momentum. Okay, normal formula is not going to work. So first of all, let us say that our v of t is the speed of dustpan down the plane. Speed of dustpan down the plane. So obviously we can write its acceleration, which will be first derivative of our velocity, will be our acceleration of dustpan. And we say that the lambda is mass of dust per unit length. Okay. Lambda is our mass of dust per unit length along the plane. And our m of t is our total mass of a dustpan plus dust collected. You can say our m of t is total mass of dustpan plus collected dust. And okay, so first of all, let's find out what will be the mass growth rate. Mass growth rate means as we are going to accumulate more and more dust, its mass is going to increase. So we are going to find out the mass growth rate. And we know that it is moving, the pen is moving with the velocity v, therefore we can write that our dm upon dt will be equal to lambda times v. And this is also, like I said, is a variable mass system, and here variable mass will be the dustpan mass. Sorry, not pen but dust mass. So we can say that variable mass system variable mass system, we can write, or we know that basic equation of momentum. We know the momentum is equal to our mass into velocity. So we differentiate it. You can say that our dp by dt will be giving us mass dv by dt plus v dm by dt, and dv by dt is nothing but our acceleration, and dm by dt we just calculated. Okay. So we can write this as our mass into acceleration plus this will be lambda v square. Now we are going to find out the forces along the inclined plane. Obviously there will be only one force on the pen, or we can see external force along the incline. External force along the incline, and that external force is, let us suppose, our F, so that will be equal to our mg, and inclination angle is theta, so this comes as a sine of theta. Okay. And so the summation of forces is equal to dp by dt. Summation of forces is equal to dp by dt. Here only force is our F, therefore we can write that our mg sine of theta is equal to our ma plus lambda v square. And in this particular question it is said that we have to solve it for a long time behavior. Okay, we have to keep in this mind. So we can say that our long term behavior and for long term behavior we can say that a large amount of dust will be collected. See that large amount of dust is collected, and the mass is growing, or rather we can say the mass will grow linearly with the distance. Mass will grow linearly with distance. And we can also say because of this linearity relationship, the acceleration approaches a constant value, which is our a. You can say acceleration approaches a constant value. Therefore, we can say that the momentum flux should be equal to the acceleration term. And mathematically, we can write this as our lambda v square is equal to m times a. And now we can easily use the force balance. Our force balance that is going to give us the mg sine of theta is equal to lambda v square. We know we already calculated is equal to over ma. So this comes as our ma plus ma, giving us 2ma. Okay, and from here we can just say or write the equation of acceleration. So acceleration will be equal to mass, and mass cancels out. So this comes as over half g sine of theta. So this will be our acceleration after a long period of time. Okay. So this completes all the 5 questions for today. Okay. And in the last lecture or last video, we also solved some question of our variable mass system, and there also we used the rate of change of momentum is equal to the summation of forces. Okay. Because the mass is going to continuously change, therefore it is a little bit difficult, or rather it is not, we cannot use force is equal to mass into acceleration, because our mass will be a variable mass system. Okay. So in this in today's part, we solved that the mass variable system need not be in vertical motion, it can also be in a horizontal motion. But the equation of summation of forces will be equal to a rate of change of momentum will be always applicable, whether it is moving in vertical or it is moving in a horizontal part. Okay, and in this particular question, it was moving along a slant. Okay. But this equation is valid whenever there is our variable mass system. So this completes all the 5 questions. Thank you.